Yes, thanks, Aki. So I'm going to give a presentation on the calibration of high contrast imaging data, specifically talking about how we calibrate the measurements we make within our observations and why this is important for interpreting the results. So I thought I should start with quite a basic question of what do we actually want to measure in our images? So we can produce these really beautiful images of exoplanetary systems, such as this animation of the 8799 system with the planets orbiting the host star. But what specifically do we want to measure? So there are two main things we want to measure. The first is the position of the planets as a function of time. It's called astrometry. And this allows us to determine the orbits of the planets, to measure their orbital properties like the inclination, eccentricity. And also it gives us clues as to the formation mechanisms for these planets, allows us to investigate maybe planet-planet interaction, mutual gravitation, or planet-planet disk interaction. And then there's photometry and spectroscopy. So at the bottom here, I have an animation from GPI showing the 51 Eridani planet in the H band. And you can see in the blue part of the spectrum, we have emission from the planet and then a strong methane absorption feature in the red half. And so by measuring the flux of the planet as a function of wavelength, we can get information about the atmospheric properties and understand more about the formation of the planet. So for astrometry, we're actually quite good at measuring the position of the planets within our reduced images quite accurately. So I'm just showing here the data, a best fit model, and the residuals to that fit. And you can see that the fit is pretty good. We can measure this to well below a pixel precision, but on its own, this value is actually meaningless, right? It's just a measurement of the position of the planet on the detector. What's missing here is information about where the star is. So you see it's been cleverly occulted by the chronograph here in the image. And also, how do we transform from detector offsets in pixels into offsets on sky in angular separation? And also accounting for the rotation between the detector coordinate system and the celestial coordinate system. So this conversion can be distilled down to a rather basic equation, taking our measurement of the location of the planet in pixels, the location of the star in the same image, and then some scaling factors to convert between arc seconds or pixels and arc seconds, a rotation matrix to account for this rotation between the coordinate systems, and that gives us our on-sky angular separation. For photometry, it's quite similar, right? So we can fit a model to our planet's PSF. We can measure it to reasonable precision, but again, the number we measure is actually quite arbitrary. So we have 4 data number or 4 ADU in this planet, but it's meaningless on its own. We need to know how bright the star is and how we can convert from the flux ratio to the absolute flux. And again, the relation is relatively straightforward, right? So we have the flux ratio between the planet and the star in the same image, which is critical, and the absolute flux of the star, and the product of those gives us the absolute flux of the planet. Okay, but before we dive into those two different topics, I'm going to first talk about the data reduction and the initial calibration that we need to do. I'm going to talk about imaging in a single filter. So this can either be narrowband or broadband, and then some discussion on integral field spectroscopy. And that provides low or medium resolution spectra over a smaller field of view. So for imaging, we follow the standard near-infrared data reduction pipeline. This has the typical dark subtraction, flat fielding, bad pixels correction. And this is typically handled by instrument-specific pipelines. These are maintained by observatories, instrument consortia, and possibly even by the community. And this step is often not handled by your favorite PSF subtraction toolkit. So PyClip that you used yesterday doesn't handle this step of the data reduction process. But the idea is to convert your raw image, which has many cosmetic artifacts in it, into a clean image that you can use for your PSF subtraction. And this step also accounts for the differing sensitivities of the pixels. Also at long wavelengths, this has been mentioned before in previous talks, that we have a problem with the sky background at long wavelengths. So what I'm plotting here is the thermal emission in photons per second per meter squared per micron per arc second squared. It's a very complicated unit as a function of wavelength. And if you compare between the K and the N band, you can see there's a 100,000 times increase in the sky background. So this is very problematic in terms of detecting faint objects in the thermal infrared. And this is demonstrated here with an example of one star being observed in the H band with a 0.1 second exposure, and then at the L band with the same exposure time. But you can see that the sky background is massively increased, such that the star is not barely detected, but it's the detection is at much lower significance. And so you can deal with this problem by, okay, so the basic way of dealing with this is by constructing a mean sky background from all your sky frames you obtain and then subtracting that from your science image. But you can do an optimal combination with PCA to find the best combination of your sky frames to improve the final detection significance. And so this can be done. The success of this kind of depends on the observing conditions, but this one example from NACO with N-band data shows that you can achieve a significant improvement in the detection of the 3 planets in the 8799 system. Okay, then moving on to the IFS, the integral field spectroscopy. As I said, it provides this low and medium resolution spectra. It does this by putting the field of view through a lensed array. These lenslets focus the light, which is then dispersed on your detector, and then some magic happens here to reconstruct your data cube, which has an X and Y, the standard spatial scale, and then the Z-axis is the wavelength. So just showing you an image without the lensed array from sphere. The detector here has just been illuminated with a quartz halogen lamp, I think, or a flat field lamp. And then if we introduce the lensed array, you can see that flat illumination has been replaced by all these hundreds or thousands of microspectra. And if we zoom in, each one of these contains the spectrum of that point in the field of view. So with these data, we need to follow the same near-infrared data reduction pipeline steps, like the dark subtraction, etc. But we also need to identify where these microspectra are and what the mapping between pixels and wavelength. So to do this, we take images with a flat field calibration lamp on the left here, the one you saw earlier, and then one with either an arc lamp or a laser source at different wavelengths. And the combination of these two provide both the position of the microspectra and a wavelength solution for each of the microspectra. So we take that solution, we use it on our on-sky data. This is data from a star near the center of the PSF. And this is the variation of the flux of the star at this pixel. And we want to extract the spectrum from this pixel. And we can do this either by a really basic aperture photometry, where we just basically sum the flux along each of the rows within the microspectra, or we can use a more complicated forward modeling based approach using a model or empirical PSF to better reconstruct what is the underlying flux distribution that produced this image. And this can help, especially if you have microspectra that are very closely packed, where you might have crosstalk between neighboring microspectra. Okay, so we have our reduced images. You can see either imaging data on the left here or IFS data on the right. But you notice in these images, although it looks like you can see the star here, it is actually occulted behind the chronograph and you cannot directly measure it. And the same is true for the reduced data we get out of the PSF subtraction process, right? So we see clearly the detection of the planets, but the star remains occulted. And this was discussed in Faustein's talk. So the question is, where is the star in this image? And so one way we can measure the location of the star is by taking advantage of the behavior of the image when we start to adjust the amplitude and the phase in the pupil plane, as was discussed on the first day. So in this simulation here, I'm showing an off-axis telescope, just a circular pupil, and the resulting image in the focal plane. If we introduce a reticulate pupil mask into the pupil plane, we can see that in the focal plane, we've generated replicas of the central point source in a periodic pattern, moving away from the star. If we rotate the angle of the mask in the pupil plane, it rotates the position of the spots in the focal plane. If we adjust the spacing between the wires in our grid, it moves the spots in and out. And if we adjust the thickness of the wires, we can control the brightness of the spots. So you see here, as I make the spots thicker, the satellite spots around the central star get much brighter. And we can take advantage of these three properties to design a pupil mask to put in our chronograph or in our optical path to generate these reference spots, which we can use to calibrate the position and the brightness of the central star. So this is a more realistic simulation. On the left column, I have the pupil plane and focal plane from GPy without the wire grid, showing just like a standard chronographic PSF. But then if we introduce the wire grid, the satellite spots appear at a flux ratio about 1 in 10,000 compared to the peak brightness of the star behind the mask. And I'd encourage you to look at this paper, which I've linked into the slides, which contains all the gory mathematical details of how they came up with this idea of using this reticulate pupil mask. So on sky, this looks like this. I think we actually saw it in the Mageo data on the previous talk as well, but you see the satellite spots around the central star, and these increase in distance away from the star as a function of wavelength as you move through the data cube. And that's just because this is a diffractive property, so it scales as a function of wavelength. Instead of varying the amplitude, we can also, or instead, vary the phase in the pupil plane. So we can introduce an optical path difference in the pupil plane to generate calibration spots in a similar manner. So what I'm doing here is putting a sine wave on the DSM, and you can see as I increase the amplitude of the sine wave, the amplitude of the spots in the focal plane increases. Similarly, if I vary the angle of the sine wave, it varies the position of the spots. And if I vary the frequency of the sine wave, it moves the spots in and out. So we can use these three properties to design a pattern, effectively, to put on the DSM or the DM to introduce these spots artificially into our data. So once we have these spots, then it's actually quite trivial to locate the star, right? So we just fit a Gaussian to the 4 spots, connect the pairs, and then the intersection of those gives you the location of the star. And this is a really accurate way of measuring directly where the star is. I should note for other types of chronographs, they may not use the same technique, but it's kind of similar. The approach is similar for at least some of them. For example, for the APP chronograph, the design of the chronograph is such that it produces this calibration spot at a very well calibrated distance between the two PSFs and a well calibrated flux ratio between the unocculted star and the calibration spot. But the principle is the same here. It's a calibration spot we use to calibrate the astrometry and photometry. For the vortex chronograph, we can actually measure from the brightness distribution of the light around the vortex to directly infer where the star is under the or within the vortex. So on the left here, it's a misaligned PSF, and as we move to the right, it becomes aligned. And the flux distribution around here gives us information about the location of the star. And for the planet, okay, well, that's relatively simple, right? So we did that yesterday in Faustein's talk, talking about forward modeling or negative planet injection techniques. So as I showed here, this is just the data and the model and the residuals. So we can measure this quite easily, quite accurately. And then once we have this relative measurement of the position of the planet relative to the star, we can then use the detector plate scale and the rotation matrix to derive the final astrometry. I should note that this equation assumes you've already corrected all the higher order optical distortion within the instrument. So this is effects like pincushion, where you have some strange optical distortion on the detector. This is typically measured it's measured during commissioning and then maybe irregularly afterwards in routine calibrations. And this can be done with a pinhole mask, where you have a mask that has pinholes at a very regular grid with regular spacing. We image this mask, and then we can measure the spacing between all these spots on the detector to remove these higher order distortions. But this doesn't give us the absolute calibration on sky, right? Because it's just internal to the instrument. So to link it to the celestial coordinate system, such that we know where north is in our images, we take data on astrometric fields, typically globular clusters. This is a nice image of 47 Tuc from Sphere with one of the stars behind the chronograph. And then we compare the pixel positions in our Sphere data or in our imaging data to catalog values from Gaia or from HST, for example, which has very, very well calibrated astrometry. And then we can compare, or we can very easily derive what is the plate scale from the comparison between our pixel positions and the catalog values. So it's a simple set of linear equations. For instruments with smaller fields of view where you can't actually access the full globular cluster, so this is an image about 15 arc seconds on the side, so it's quite large. But if you have a very small IFS with a few arc seconds field of view, you typically rely on calibration binaries or asymmetric binaries. So one example here is the theta 1 B in the trapezium cluster. There are 4 stars which we can use to calibrate the plate scale and the north angle. But the key thing to remember here is that the stars in the system are actually orbiting one another. So we need to account for their orbital motion between our measurement with a well-calibrated instrument and our measurement taken with our new instrument that we're commissioning. So the plot here just shows the position angle as a function of time changing quite significantly for this one binary system. And then now we have all the pieces put together. We have the relative position, we have the plate scale, we have the rotation matrix, and that gives us our on-sky angular separation, which is very well calibrated. And having a well-calibrated measurement means we can combine data taken from different instruments and build up these very long time baselines we need to perform studies on these planetary systems. So for the 8799 system, we have data going back to, I think, 1998 up to the present day. But these are taken with a variety of instruments. It was very important to calibrate them very robustly such we could combine the data together. Okay, then moving on to the photometry, well, the story is actually pretty similar here. So this, again, the star is occulted behind the chronograph. We can't actually get a direct measurement of how bright the star is. But we can again use these calibration spots to infer how bright the star would have been had we seen it in our image. So as a reminder, varying the thickness of the wire grid we use or varying the amplitude of the sine wave on the DSM controls how bright these calibration spots are surrounding our central PSF. To calibrate the calibration spots, this can be quite difficult because they tend to be very faint relative to the star. So it's very difficult to get an image where you can see both the central star and the calibration spots. So they tend to be 1,000 or 10,000 times fainter. You can use the internal calibration source of the instrument and then like a series of exposures with a ladder of exposure times to get to measure both. Or you can use, as is the case here, a high flux ratio companion with a known brightness that you can directly calibrate the spot brightness on sky. Another technique to use here is an off-axis PSF measurement. So on the left, I'm just showing a chronographic image from sphere with the star, again, occulted here, although it looks like it's visible, it's actually occulted. If the star was off-axis, it would definitely saturate here and be impossible to measure directly the flux. However, if we introduce a neutral density filter, which attenuates the flux quite significantly and reduce the exposure time, we can get a direct off-axis measurement of the star. However, to determine how bright this star would have been had it been taken without the ND filter in this image, we need to know the transmission of the ND filter as a function of wavelength. And so that's what's plotted here, transmission versus wavelength. In this case, it's a few percent in the near infrared. And then for the planet, well, again, it's the same. We use the same forward modeling or negative planet injection techniques to derive the planet's flux in data number or ADU. And this can be then compared to the stellar flux. We have to account for 2 throughput terms in our calculation. We have to account for the chronographic throughput, that was discussed by Chris in his previous talk, where there's not a sharp edge in the transmission of the chronograph. It doesn't go from 0 to 1 instantaneously. It varies smoothly as a function of radial distance. And we have to also account for the algorithmic throughput. So this is the flux we lose when we do the PSF subtraction. And we can calibrate this by injecting point sources of known brightness into our image before PSF subtraction, run our PSF subtraction process, and then recover them and measure the flux. And the ratio of the injected to recovered flux gives us the algorithmic throughput. Okay, so once you have your planet flux, you correct it for these throughput terms, you have your flux of the star in the same image. Now we just need to get the absolute flux of the star. Now, if we have broadband data of our planet in the JHK bands, it's relatively straightforward. We can just go to Sinbad, type in the name of our star, look at the flux from 2 mass, look at the parallax, and then use these equations to work out what is the flux of my star in some physical units that I can use to compare to compared to atmospheric models. This does require knowledge of the 0 point of the filter system we're using. So in this example for 2 mass, this is the flux of a 0th magnitude star in watts per centimeter squared per micron. But similar tables exist for other filter systems, systems as well. But as I said here, this is only useful if you have broadband photometry in JHK. If you have measurements in other filters, like a narrowband filter, or if you have spectroscopy, then you just can't go to Sinbad and just take that value. For photometry, you have to use color transformations. This relies on certain assumptions of the underlying flux distribution of the planet, and this can introduce a significant error if you were to use these without properly accounting for this. For spectroscopy, you could use a black body. This is typically okay if you're looking at very hot stars in the infrared, but this doesn't work so well for M stars where you have significant absorption in their spectra. The best approach actually for both is to use a combination of atmospheric and evolutionary stellar models fit to the literature photometry such that you can estimate what the flux would have been for the star in your filter or over your spectral range. So just an example here, this is for one star with, I think, Gaia photometry up here, or maybe Gaia and Hipparcos photometry, and then 2 mass photometry here. And then the underlying curve is the best fit from our joint atmospheric and evolutionary model grid. And what we can do is we can just ask the question, okay, what would the flux be in the L and the M band down here? Or what would the flux be over a range at a given arbitrary resolution? So I could do either a low resolution, maybe R of 100, or even R of 100,000 if I wanted to. Just depends on how high resolution your spectral grid is. So then, with all this information in hand, we can then compute what is the absolute flux of the planet. We can take the throughput corrected flux of the planet. So this is the flux of the planet in data number divided by these throughput terms. We then have the flux of the calibration spots or the off-axis image multiplied by this scaling factor, which accounts for the grid ratio or the ND transmission, for example, and then multiplied by the estimated absolute flux of the star. And this gives us the flux of the planet at the wavelength we desire, or over the filter bandpass we desire. And again, like for the astrometry, this is important if you want to combine data taken with different instruments. So here there's an example showing data taken with the Sphere IFS, combined with longer wavelength data taken, I think, with the NERC2 camera on Keck. So to be able to combine these data together into a single data set, it's very important to do your calibration correctly, such that you can compare them without introducing any systematic biases in your analysis. So in conclusion, I just hopefully made the point that the calibrations are important and that actually the observables we measure directly in our image are meaningless without them, right? So it's the planet pixel position doesn't mean anything, nor does the count rate in data number. It's what you do with that number and how you combine it with your information about the host star, which is important. Careful calibration is needed to compare results between instruments. This is especially true for astrometry, for high contrast imaging instruments, where there can be some variation in the north angle. And it's also very important to do error propagation from start to finish so that your position certainties are as accurate or realistic as possible. So every step along this series of calibrations, you'll have an associated uncertainty. So it's very important to take them all together, propagate them from start to finish, such that your final error bar is realistic. And I'll just end with some topics I missed completely. I didn't talk at all about polarimetry, which has its own set of calibration measurements. For example, calibrating the polarization signal induced by the telescope, and also interferometry, which is an entirely different kettle of fish, which I didn't dare even talking about in my talk. There's also reference star differential imaging. You could consider this a calibration. This is where you go off axis to take an image of another star to do PSF subtraction, but this is more of a technique than a set of calibrations. Okay, and with that, I'll finish and take any questions. Thank you.
Okay, thank you very much. Questions in the room over here.
Hey, Rob, thanks for the great talk. So you talked a lot about like calibrating or like having something like before you take your observation to help you calibrate the center star position, what would you do if you have, let's say, like archival data from somewhere where you don't have that sort of thing? Like, how would you find like the center star position in the most accurate way?
Yeah, this is a good question. Or you could think alternatively, if you had like chronographic data where they didn't use these kind of calibration techniques, for example, yeah. It kind of depends on the data set you have, right? So if you had, say, for example, thermal infrared data from NACO where they saturated the PSF, but it was still visible, you could imagine doing something like fitting the wings of the PSF with a Gaussian where you just ignore values above a certain threshold. I don't think there's a general answer to your question. It kind of just depends on what you can do. But my advice in this area would be to like test the method you're using, right? So if you do this approach, it will be best to look for data sets where you can try to estimate what uncertainty it has, such you can include that in your error budget. So you propagate it forward.
Thank you.
Other questions in the room? Or online? No, okay. Then I will ask my question. So it was really interesting. You showed a number of different technical approaches for getting the position of the star. Which one is best in your view, if you could pick any?
Yes, good question. They all have their downsides, right? So the one I was highlighting most was the satellite spots used for GPI, right? And one problem we have here is that the satellite spots are actually overlapping with the diffraction spikes of the telescope, such that there's some constructive and destructive interference, which can mess up the centroid. Saying that, I think this is a good this approach, or using the sine wave on the DSM is a good approach. And I think it's important if you want to do like precision astrometry is to use them throughout your observing sequence. So don't just take an image at the start and then stop using them during your sequence, but to leave them on continuously such that you have that reference in all of your data sets.
Okay. So this overlap with the telescope diffraction spikes, that wouldn't happen if it was, say, an unobscured off-axis telescope?
Exactly, yeah. You could get around it by rotating the reticulate mask in the pupil plane, but we didn't have that functionality in GPI. So it was stuck at this angle.
Okay, thank you.